So we want to put these pieces together that we've been dealing with. And we've talked about continuous functions, and we've talked about derivatives, but how are continuous functions and derivatives related? Well, it turns out they're really just one big piece altogether, but there's three ways of stating a very important theorem about differentiability and continuity. And the first one is that if a function is differentiable at a point, it is continuous at that point. So if you can take the derivative at the point, you are guaranteed that a function's continuous there. So that's a really strong result, because it means that we don't have to do, if we can prove things about derivatives, we don't have to do the song and dance to prove things about continuity. Now, further, if we flip this around, we say A implies B. Well, then there's a related concept that says not B implies not A. So we flip it around. So we say if it's not continuous, then it can't be differentiable. So it's not differentiable means not continuous. That's not what that means. It's not continuous implies not differentiable. And that might be a little difficult to wrap your head around. But basically, differentiability it guarantees continuity. So that means if something guarantees that and it doesn't exist, then the thing that guarantees it must not exist. That's what this means. However, looking at that, there is an open option here, which is that you can have a function that's actually continuous at a point, but is not differentiable at that point. So that's a really interesting result. And so for these last two, we're going to do some examples to show that result. The first one is that if we have a function we know is not continuous, we show that it can't be differentiable. And we're going to define this function. 1 if x is not negative, and it's -1 if x is negative. And we just want to look at this point. We want to look at when c equals 0. So when c equals 0, we know that the function output must be 1. So if we take the limit from the right, the limit as x approaches 0 from the right, we have f of x minus f of 0. And sorry, we're going to use this format. So this is yet another way to do the limits, but pretty much I only like doing this in this particular case. So I mean, you can do whatever you want, but I wouldn't recommend using this. I don't see it that often. You usually see the x plus h form more often. So anyway, by doing this, we take the function value. Well, since we're coming from the right, all the values that we're inputting are positive values. So we know that the function output must be 1. And we know that the function value at 0 is 1. So we have this 0 over x. Now you might quibble with me and you say, well, yeah, but if I directly substitute, I get a 0 over 0, and that's indeterminate. And you're right. That is a good observation. However, there's an interesting result about limits that says that if it's 0 times something, no matter what, not when you directly substitute, but if it's 0 times whatever it is all the time, has to be 0. Has to be 0. If it's 0 times every value that you put in, it has to be 0. And that can be proven, but for now, take it as gospel that that's true. So what we find is that as we approach from the right, the derivative of 0, which makes sense because your rate of change is nothing. It's a constant line. But over here, coming from the left, I have no difference in my rate of change. It's a constant line until the end. It has this spike. So it goes nothing, 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 boom. So you would expect that its rate of change shoots off to infinity. So let's see if we can verify that. So taking it from the left, when we plug into the function, we get a -1. Again, the function value at 0 is 1, so it's -1 minus 1 over x minus 0. So we end up with -2 over x. But then you end up with a positive infinity, but there's a negative there. So why is that? Well, the reason that is because we're always plugging in negative values here. So no matter what, the numerator divided by the denominator is positive, always, because it's negative divided by negative. But as this gets really small, the whole fraction, the whole output of that gets really large, so it shoots off to positive infinity. And ultimately, that's what you'll find at these jump points, is you'll find an infinity from that. And this is, some people call that like a step function. You might see something called an impulse function or something like that that's going to happen. So this comes in these things called square waves approach that. So this actually happens a lot. This is a really good model for what happens when you turn on a switch, right? You have some sort of loop, and then you connect the switch, and it couples, turns on, and you have light. So when you flip a light switch, nothing, boom. That negative there is, negative voltages and things do exist, at least from a modeling construct standpoint. But anyway, moving along, let's look at a situation where, okay, that's fine, it's not continuous, so I wouldn't think there'd be a derivative. Makes sense. But what about continuous functions? So the absolute value of x is kind of got this ricochet. And so let's talk about the origin. And we know that the function value at the origin is 0 because it's equal to whatever x is when x is not negative, and it's the opposite of whatever x is when x is negative. That way you always have 0 or a positive number. So in the case where x is positive, f of x, then the function value will just be whatever x is. And again, f of 0 is 0, and c is also, that point is also 0 here. So realistically, these two go away. So you have x over x. Well, that's just 1, so your limit is 1. Now, in the case where x is negative, the function value is negative x. So we have negative x over x. Well, those cancel. And so you have negative 1. Your limit's negative 1. Well, in these cases, your left and right-hand limits don't agree. And I didn't say that up here, but your left and right-hand limits don't agree. And if either one of those limits is infinity anyway, the derivative doesn't exist. But the left and right-hand limits not agreeing means the limit can't exist. So if the limit doesn't exist, the derivative doesn't exist because it's defined by the limit. So ultimately what I'm saying is that a function being continuous doesn't guarantee its derivative exists. But a function whose derivative does exist, if the derivative exists, it's continuous. Boom, bang, easy. And we're going to use that result when we talk about things that move along like the mean value theorem and stuff like that. So there's going to be some interesting results that come from the fact that that there's continuity implied from derivatives.